Hello there and welcome back. Today we're going to continue our discussion on polar coordinates and the double derivative. So when we work on these problems, it's important to know that a lot of times we can solve different integrals using different coordinate systems. We have the rectangular system, we have the polar system. Later on we're going to talk about the cylindrical and the spherical systems. They all depend on what we're looking for or if we have to solve these by hand. So sometimes it's going to be easier to evaluate a double integral in an alternate coordinate form. So let's take a look at how we can rewrite them. So let's look at this integral right here. We want to write this double integral in rectangular form. So you might remember a rectangular form that is having x's and y's, where the domain, the range of it, is going to be a disk of radius 2. A disk, of course, being a circle. So we want to find this volume, and this is a volume equation. So if I draw my circle, it has a radius of 2. Now in rectangular coordinate system, the top of this disk is going to be the equation y equals the square root of 4 minus x squared, whereas the bottom would be y equals negative square root of 4 minus x squared. And of course this is going to go from negative 2 to 2. So this is our base region right here. And because that's our base region, well, I know that my change in y's, I'm going to do a vertical rectangle, are going to go from negative square root of 4 minus x squared to positive square root of 4 minus x squared. My changes in x are going to go from negative 2 to 2. So how can we write our volume equation? Our double integral. Now, the change in area, remember that's my area right here. This is my little rectangular little area. And my rectangles are going to be delta y, delta x. So my dA in rectangular form is dy dx in rectangular form. So when I write this out, my function, of course, is going to be this f of x, y. I don't have to change my function because it's already in rectangular form, dy dx. And I put my domains here. My y is going to go from the negative square root of 4 minus x squared to positive square root of 4 minus x squared. And this goes from negative 2 to 2. And depending on how complicated this function is, it may be hard to solve, it may be easy to solve because of those square roots. But another way we can solve this, because I'm using a disk, a circle, I can use polar coordinates. Polar coordinates are very nice for us because polar coordinates allow us to use circles, because polars are based on circles. So how would we convert this using a polar coordinate system? Use r and theta as the limits for integration. So for this one, I'm going to start with my disk again. Has a radius of 2. But now we have to deal with r and theta. So if I look here, from here, if I draw out a radius, my r is going to go from 0 to r equals 2. So I know that my change in radius is 0 to 2. My change in theta, well, this is going to go all the way around the circle. So delta theta is going to go from 0 to 2 pi. So now I'm going to go ahead and be ready to write out my volume equation. Now this is going to be a little bit different. Because I'm in polar coordinates, our dA, remember, we're going to talk about this again really shortly in just a few seconds, is going to be r dr d theta. Remember, I looked at another video, I have a couple of other videos, and you can talk where we talk. So if you need to, take a look at those videos, or we're going to talk about it in just a few moments again. So now, I'm going to get this function right here. We'll talk about that in a second, r dr d theta. So this dy dx becomes r dr d theta. So what about the function? Well, it's no longer a function of x and y. We're using r's and thetas. So this is going to be f as r cosine theta, r sine theta is going to be our function now. Our functions of r cosine theta, r sine theta. And my change in r goes from 0 to 2, and change in theta goes from 0 to 2 pi. Now one thing I noticed is a lot easier. My domains are a lot easier to work with in polars than they are in the rectangular. But the function might be easier to work with rectangular than in polar because we have to do a little bit of converting here. All right, so let's kind of quickly review where we get this r d theta right here. we can use the simplified example to kind of figure out what the variables of integration are. Find the area of the rectangular shaped figure below. So remember, this comes from polar functions right here. Whoops, sorry about this. This comes from polar functions right here. This is theta. This would be my radius 1, and this would be like my radius 2. So I have these. So I can get my change in radius. I get my change in theta. Well, I guess this would be R1. Is the length here would be R2. There we go. I should call that one R2. There we go. So I can use this now in order to get the area of this little rectangle, this itty bitty tiny little rectangle. So it's really kind of curvilicious because it is a sweeping motion. It's a circular. So it's really kind of a little bit of an arc right there. But if you go really small, it becomes more straight. Remember, in calculus, we study with tangential lines of functions, where in an instantaneous moment, anything curvy is actually a straight line. And that's kind of what we're doing, and that's what we're kind of saying here. If this rectangle is small enough, this looks like this rectangle. This becomes this rectangle, this little area right here, this area that we're looking at becomes a rectangle. It becomes a rectangle right there. So let's take a look at that little rectangle then. This little region right here, this is part of an arc. And how we get the length of an arc in calculus, in pre-cal, was S equals R times the change in theta. R dr theta. You remember that from pre-cal, hopefully. This length right over here, well, that's just a difference in my two radii. So that length right here is delta R. It's my change in radius. So I can say the area of my rectangle is R delta theta delta R. Now, we're going to want R first, just because that's normally the way we integrate this. So we're going to write this as R delta theta. Now, that's the area of one tiny little rectangle. But remember, we're going to go crazy, and we're going to let delta R and delta theta go to 0. So they're going to get really small. The smaller they get, the more accurate that rectangle becomes in terms of looking at the area. So, and as a result, our area, now our change in area, our little minor change in area, dA becomes R dr d theta. And there is our equation. So to get the area of the whole is going to be the integral, given a little domain, R dr d theta. And there's the equation for our area formula for using polar functions. All right, go on to video number 2. We're going to take a look at some examples.